Hello, and thank you for being here. Today I'm going to talk about the Materialization Engine backed by Apache Flink for the purpose of data integration in event-driven microservices architecture. I'm going to show how this solves a data integration problem in this kind of architecture, taking data from a central event bus and materializing it to persistent S3 storage for later data integration into relational data warehouses. So let's start. Let's start with the agenda. First, I want to introduce Zalando's microservices architecture, and then I want to state our data integration challenge. Then I'm going to introduce our materialization engine, the Flink Backend, feature we call stream compaction. And finally, I'm going to compare our current approach with the old one. But first, I would like to introduce myself. I'm Mihail Vieru. I'm a big data engineer in Team Flux of the data engineering department of Zalando. Something about Zalando. We are Europe's leading online fashion platform. We are active in 15 countries. We have 21 million active customers. And last year, we had a revenue around 3.6 billion. We are selling 250,000 products from 2,000 brands, and we have roughly 13,000 employees in Europe. From those 13,000, we have 1,800 tech employees coming from 77 nations, and we are located in 6 tech locations with our headquarters in Berlin. We're working on homebrewed, cutting-edge and scalable solutions. And if you'd like to find out more what we're doing, I would invite you to visit our page, tech.zalando.com. So now let's have a look at our microservice architecture. So we have microservices which implement their own business logic, and they have their own persistence layer. They all use central event bus we call Nakadi, which exposes the REST API. And this communication is also sometimes important for analytical purposes. So sometimes we want to integrate those events used for communication also into relational data warehouses for analytical purposes. Last but not least, everything runs on AWS. So a bit more about Nakadi. It's our central event bus. It's a distributed event bus that implements a RESTful API abstraction over Kafka-like queues. Currently, it's implemented with Kafka. There's also ongoing work on Kinesis. We have thousands of Kafka topics with a high variance in event structure, size, and throughput. I would like to emphasize now the event structure. So we have very complex ones for some certain event types. We have nested events with arrays within arrays and so on and so forth. And as a consumer, you can specify the partition offsets and the batch size in your GET requests. This is open source, of course, and if you like to try it out, just download it from GitHub. Yeah. Now let's come to the data integration challenge. So as you can see, we have on the left-hand side our microservice architecture for the operational systems. On the right-hand side, we have relational data warehouses like Oracle, Amazon Redshift, and other relational database management systems. For instance, business intelligence is heavily relying on Oracle. So we want to bridge this gap. So what are the requirements? Our goal is to consume data streams in a relational database-friendly way. We want to materialize data from Nakadi for the Nakadi central event bus into cloud storage and transform the aforementioned complex JSON events into easily ingestible CSV files. Also, by doing so, we want to flatten arrays present in some complex structures. And while we are doing this, we also want to relieve load on the sometimes monolithic data warehouse by compacting event streams according to event properties. I'll come to that a bit later. So let's have a look now our Materialization Engine, which wants to solve this thing. So it's it's between the operational systems and the analytical systems, and also provides a RESTful API. The relational data warehouses can call it, and the Materialization Engine backed by Apache Flink then persists data into Amazon S3, and from there the data warehouse can download the files and integrate the data. Let's see how this happens in more detail. So how does it work? On the left-hand side, we have the client, the relational data warehouse, and on the right-hand side, we have the source, the Nakadi central event bus. So first, the client issues a request to our request handler. The request handler also has a configuration manager implemented in Zookeeper, which stores some mapping information, for instance, from complex JSON structures to CSV flat flags. So there you can store, for instance, which fields do you want from those events and in which order. Then our request handler calls Flink's REST API, which in turn deploys a job to materialize data from Nakadi to S3. After this is done, so something to mention here is that our request handler is also periodically checking if the jobs are done or not, and then issues a stop request and returns to the client with a set of files for which the client can later download. So we see the Materialization API as another abstraction layer over Flink's REST API used to deploy, monitor, and control jobs. And as I said, our configuration manager stores per each Nakadi topic JSON to CSV mapping, the partitioning key, and the ordering key, which is relevant for compaction, as we'll see later. So now, what is it? Let's look at the Flink Backend. So we have short-lived stream-to-batch jobs. We deploy one job per call. We implemented a stoppable Nakadi stream source, which we use to gracefully stop the jobs. So if there are still events there, inside the job, we want to wait until those are persisted and then stop it gracefully. And we implemented a modified bucketing sync for the S3 Frankfurt region, which writes the files to the test manager's attached EBS storage and moves them to persistent S3 storage later. We've done this in order to circumvent a known problem with Flink's S3 connector, because Flink uses for S3 connector the Hadoop file system implementation. And in the Frankfurt region, there's a bug with a signature version for authenticating requests. In Frankfurt, only the version 4 is available, and Hadoop 2.7, which against Flink compiles, has an issue with it. In Hadoop 13324, you can read more. You may ask why didn't we just compile Flink against the next Hadoop version? As the previous speaker said, you want to have the official releases in production. You don't want to have forks for which we don't have the resources to maintain. So basically, what we're doing is batch processing using a streaming API. So we at the switch of a button, we can use the same jobs and have them long running. So how do we ensure when we want to stop a job? So our Flink jobs expose the progress for accumulators. Some of them are the following. So we have the number of Nakadi consumers which you have finished. Imagine the following. We deploy a job for a topic which has 8 partitions. Then we have 8 concurrently parallel running instances of Nakadi consumer, and we want to see how many of them have finished. Then we have the number of events we have read from the central event pass, and the number of files delivered to S3. These are quite self-explanatory. So the Materialization API periodically queries Flink's REST API to measure progress, and after all these conditions are met, then the job is stopped. Yeah. So a bit about the cluster. So we use Flink in standalone mode inside Docker containers on Amazon EC2 instances. Right now we're using T2 large. And some cluster specifics, we over-provision test managers because we need the test slots. We have roughly 80 data integration pipelines running. And if the client wants to materialize all this data, then we have to provide the resources. Right now, we also implemented upscaling on test slots via CloudWatch metrics. So we can easily add more workers to the cluster. Downscaling is still an issue, which we're currently working on, because we cannot just kill worker nodes. We have to check first if there are some jobs running there. So now let's move on and to our string compaction feature and see how we relieve some resources on the data warehouses using this thing. So our goal is to relinquish data warehouses, data warehouse resources by reducing the size of the data we ingest. Some streams can be compacted, and for some streams, for some events, analytical systems are on the analytics side, they're only interested in the last value. Consider the following stock information. So we have here some Nike sneakers with a certain article ID and in a different version, available in a different quantity. So first we had 50 Nike sneakers available in our warehouses, and then we get an event that we only have 30 left. In this case, what we want to get at the very end is just the last event. So, so this string compaction can be applied to events which represent changes to this same resource. So here we have the same partitioning key, but version as a different ordering key. How we implemented that? The implementation is very straightforward in Flink. So first of all, we deploy Flink jobs with configuration as parameter from the request handler, and in this configuration it's also the aforementioned ordering key. So we compile the stream according to them. So we key by the partition key. We have a session window and processing time, and then we reduce a stream. Yeah. Also, the session window can be specified by the client, so the client can also specify for how long this may happen. With this, we achieve for some topics compaction rates up to 70%, so only 30% of the stream is materialized, and this helps the data warehouse process less resources. So we also have out of order events, as you probably all of you know, that were not received in order we expected. So we have the higher version first, and we materialize them in a different file. And we let the handling of those out of order events to the relational data warehouse. So here let's have a look at the import process. After the call has been finished, then the data warehouse downloads some CSV files on its server, and we have one file per partition and one corrected file per partition. So we have these sets of files which are mounted as external tables, and from there we create a view from the main where all the records from the correction are, and all the main that are not in correction. And from there, with this view, we via a processing statement like a merge statement, we merge them into the operational data store layer. Finally, I would like to show what we gained by doing this approach. First, I would like to show our old architecture. So previously we had our own Kafka queue, we have an importer written in Python, we had separate ATL jobs in Flink, and from Kafka we had a Java written exporter. which also had had a configuration manager. From there, persisted to S3, and from the S3 to relational data warehouses. So as you can see, lots of stacks. So right now we had instead of the Flink instead of the importer, the Kafka Flink exporter API and Zookeeper, we only have 3 stacks. We reduced our AWS costs. We decreased our operational overhead because we don't have any more data redundancy in Nakadi and Kafka. We don't need to set up the importer, and of course far less maintenance because we don't have these long-running ETL jobs. Last but not least, I would like to emphasize the advantages using Flink's API. It allows us to easier reason and implement certain features, like the compaction. As you can see, we had only 3 operators, and before using Flink, so using only the exporter written in Java, it was quite cumbersome. It used the Kafka low-level API, and it was very hard to maintain. Of course, also by using Flink, we have now an extensible feature set, so we can always add more features to this materialization engine. We can add, for instance, filtering on events, pre-aggregations, and so on and so forth. So, thank you for your attendance. Do you have any questions?
Hiya. You mentioned that you handle out-of-order events, and you're doing it in processing time. Is that?
Yes, in processing time. Yeah, because we leave, as I said, we leave this handling of out-of-order events to the data warehouse.
All right, thank you.
Maybe just a follow-up. Why not doing in Flink so ordering by event time? Could it be a solution?
Yeah, it could be a solution, but we had this before. So we had a client written in Oracle in PL SQL, which used the legacy approach, and in order not to change the old client in Oracle, or to keep the changes minimal, we decided to have the same logic. But yeah, that's correct. Could be something to think of.
Thank you. Regarding the compaction,
yes.
Couldn't you leverage Kafka compaction as well? I know that you just got rid of Kafka, so probably you don't want to use that. But do you have such a compaction feature also in Nakadi that could do that?
No, there's no such compaction feature in Nakadi, so this is why we're implementing it with Flink.
All right, thank you.
Are you planning to also do the business intelligence queries in a streaming fashion in the future?
We have some ETL jobs, but what do you mean by business intelligence in streaming fashion? So do you mean like broader architecture change so that everything is stream, or?
Well, basically, for example, get rid of the Oracle database currently storing.
Yes, that will be very hard because we have a very big business intelligence department. And we have a lot of analysts there which rely on it, which are proficient with it. So basically we would have to provide the same features. Of course, some declarative language support like SQL. So this would be quite a challenge.
I imagine, yeah.
But currently there are no such plans.
Thank you.
Could you give us a rough overview of how the REST API is implemented?
It's implemented in Spring Boot. And basically, so the client keeps all the stateful information. The client knows about the offsets, knows about the partitions, knows where it left off, and in the next call, it will issue a call with different parameters. So basically, our REST API is stateless. And then it deploys a job according to the client's request.
We're slowly running out of time, so last question.
Is there any special reason why you wrapped your whole Kafka-based event bus in a REST API?
Wait a second. To show you the slide.
Don't talk directly to Kafka?
Yes, I believe this is a very good question. To keep an exception over Kafka-like queues. So we don't want our clients, we don't want the microservices to be bounded by using Kafka. As I said, in the future, also the backend of this unified, of this central event bus could be as well a Kinesis. Yeah. Okay. Thank you very much.